And this pattern I call 1 by 2. Okay? That corresponds to one terrace area. Let's say one of my terrace has 1 by 2 arrangement. The other terrace has 2 by 1 arrangement, and the terrace is very small, right? Because they are of the order of nanometers. My electron beam is very big, of the order of millimeter. So I sum up all these different terraces in my final Lie pattern. And what do you see? You will see an overall pattern with both the square and the triangle, right? So you see weak spot, which exactly look like the 2 by 2. Which really, you could have 2 domain, or in this case 3 domain, because you also have this circle slot, right? I say 3 domain that that make up the 2 by 2 pattern that you see. Yes.
So when you're defining a 2 by 1 or a 1 by 2, the first value is the x direction?
Yes.
Okay.
Just pick any one direction, any unit vector. So the unit vector you define arbitrary with reference to the substrate spot, substrate vector. Okay.
So then really the triangle is a 1 by 2 and the square is a 2 by 1.
Yes, you can call it that.
Okay.
It doesn't really matter. What I really want to show you is that 2 by 1 plus 1 by 2 give you the same Lie pattern as a 2 by 2.
Okay.
Right? That's is really just my point. And you cannot distinguish them. So I'm trying to point out the limitation of the Lie pattern, because you cannot tell just by looking at the Lie pattern whether you have a true 2 by 2, right? Or you have different domain consisting of 2 by 1 and 1 by 2. Okay, so that is my point. So here is a different drawing of these 3 domains that I see. This is real space. Okay? And this is my 2 by 2 patterns that you see. You can see if you have 3 different domains or terraces, if you like, then you have no way of knowing whether you have 3 terraces like that or a single terrace would overlay like this. Okay? So there's ambiguity, right? So the point is that there's ambiguity even in pattern recognition with the Lie pattern that you see on here. And sometimes it could be much worse. In this case, you have a very complicated Lie pattern that look like this, which is due to 2 domains. So this is actually what you see. Here I'm trying to draw domain 1 going this way, domain 2 going this way, and the 2 overlap. What you actually see in the Lie pattern is an intensity like this, and the 2 domain. The intensity alternate as you change the kinetic energy, right? It's alternating. So in these cases, it's very complicated to figure out what you got actually on the surface, even though we have night diffraction pattern and the intensity variation associated with those sub-patterns that you see. You have one set of sub-patterns represented by the black dot, another set of sub-patterns represented by the open dot, and the actual thing you see is like this, alternating intensity like this. So for real space, so my lesson here is to say that for real space, the present domain and anti-phase domain complicates the appearance of the Lie pattern because of this coherent interference that you are basically summing whatever you see, and it becomes quite complicated.
So the domains are different terraces?
Domain are different terraces, or they could be just different part of your domain with different structure. Terraces is a flat area of the surface,
Right.
but the flat area does not all have to be of the same crystal structure, right? So you could have, for example, this is my terrace, okay? My terrace are building, so these are all flat, and all of a sudden you miss an atom, right? you're building your element and you start growing this way, and then it meets, right? And then you have so-called anti-phase boundary. So this is still flat.
Yeah.
It's just anti-phase boundary. So you miss one atom, and then you have this so-called anti-phase boundary on here, and this is still called terrace, and this is called domain 1 and domain 2. Okay, so that's all it is. The domain just a structure with the same crystallography, same crystal structure. Okay. So here I'm trying to show you a C2x2 pattern that I got, right? And here I'm showing real space. Real space. You can see the black dot is my substrate atom. The chronosis is my adsorbate atom. Okay. And this is a C2x2. Why? Because this is 1 by 1. The black dot is 1 by 1. This is my 2x2, right? Because you have 2 units of the black dot. And you have a center atom in the middle, so that's why it's a center 2x2 for the overlayer, right? And then, so this position you sit at the so-called 4-fold hollow site because it's got in the middle of this. These can also sit in the bridge site. This is one bridge site, this direction, or in the other bridge site, like this. And these two, all three of these, you can see, this is still a 2x2, isn't it? Right? Here I'm talking about the local structure is in the 4-fold hollow site. This is a bridge site, this is another bridge site. But the lead pattern is still 2x2. You can see this is 2 unit, and there's a center. And this is also 2 unit and 2 unit in the center, like this. Right? Like this. So what does it mean? It means that I cannot tell you, right, even though I see a 2x2 pattern, I can tell you the local structure from the pattern alone. Because it could be in a 4-fold hollow site, or it could be in the bridge site. They both of them, all three of them, give me the same 2x2 pattern. I don't know exactly where the bonding site is. I know the arrangement of them, how they space with respect to each other. I don't know precisely the local bonding structure. Okay, that's another limitation when I see a lead pattern like this. Okay, so my time is up. So I will try to finish up about talking about lead. I only have a small topic to cover, and then I can talk a little bit more about other surface structure determination